The objective of this talk is to illustrate how to compute crack growth in adhesively bonded joints under representative operational flight loads. This work was supported by a US Navy ONR NICROP grant. The problem space that we're considering is aptly illustrated in Figure 1. This figure shows the in-service disbonding and delaminations that have been found in US Navy and Royal Australian F-18 aircraft. The figure is of a cross-section of a titanium to composite joint which occurs in the inner wing of the F-18 aircraft. You can see cracking that has extended around the joint, delaminations that have occurred in the composite, and the outer mold line is missing. If you find damage in a service aircraft, you need to ask, is it statically safe? What's the residual strength of the damaged part? Will it grow under representative flight loads? If it grows, what's the remaining life of the part under the actual flight load spectrum? No standard 1530D requires that the science base used to answer these questions is based both on conservative delamination, crack growth thresholds, and on conservative delamination, crack growth curves. In this context, the United States Composite Materials Handbook, CM817-3G, explains that, given the increased scatter in both strength and fatigue life, special considerations must be given to the fatigue durability design of composites and bonded joints. Note the word increased scatter. How to account for this increased scatter is a feature of the presentation and is fundamental to MIL Standard 1530D. MIL Standard 1530D and also Joint Services Structural Guideline JSSG 2006 state that building block test programs shall include sufficient testing to characterize the effect of material processing and manufacturing variability. Let us next address the fracture mechanics tools that are used to assess crack growth in adhesives. The parameter delta G is the most widely used crack driving force. However, expressing the ADN as a function of delta G, where delta G is the difference between the maximum and minimum energy release rates in a cycle, can yield anomalous, erroneous results. In this context, the 1965 paper by C. Paris and Irwin was the first to give the solution for the crack tip field in a composite structure. This seminal piece of work revealed that the crack tip stresses were governed by the square root of G. This naturally leads to the use of delta square root G as the extension of the Paris growth law in metals to composites and bonded structures. Important thing to note here is that it is delta square root G and not delta G. When you do this, many of the anomalies that you'd seen before vanish. This leads us to discuss the equation that should be used to compute crack growth in adhesively bonded structures. The equation that we will use in this paper presentation is given on this slide. This relates dAdN to delta square root G. This is because the crack tip stress field is governed by square root G. In this equation, N and D are constants, and A is the cyclic fracture toughness. The term delta square root G threshold is the associated fatigue threshold. For delamination and crack growth in composites and adhesives, the terms D and P are independent of the mode mix, and P normally lies in the range of approximately 1.7 to approximately 3.
This equation was developed by Professors Hartman and Shivey at Delft for crack growth in metals. It has been shown to have the following features: an ability to accurately compute mode 1, 2 and mixed mode delamination growth and crack growth in adhesives using a single equation, with the exponent and the constant of proportionality being independent of the mode and the mode mix. An ability for a given cramination length to account for the associated variability via a single parameter, namely the fatigue threshold. This simplifies the risk of failure assessment that's inherent in Mill Standard 1530D, CMH 173G, and JSSG 2006. It enables the worst case mean minus 3 sigma crack growth curve needed for economic life assessment to be determined.
To illustrate what we've just discussed, namely how it can be used to compute the mean minus 3 sigma curve, which is needed for a durability economic life assessment, let us consider the example that's been presented by Professor Kinloch in this conference on delamination growth in IM7 9773, which is a composite material that's used in the F-35 and in the Super Hornet. This figure shows a series of delamination growth curves where the ADN has been plotted against Gmax. These curves were performed at various levels of GC, the static fracture toughness, and as you can see, there is a wide variation, lot of scatter you might say, or variability in the growth curves. Each one of these curves can be accurately captured by the Hartman-Shivey equation that we've mentioned, and consequently, we can determine the variability both in the threshold and in the toughness. This enables us to determine the worst case, the mean minus 3 sigma crack growth curve that you need for your assessment. The next example that we will discuss is the variability in crack growth in a rubber toughened epoxy film adhesive, namely EA9628. Again, we see that each one of the curves is captured very well by the Hartman-Shivey equation. In this particular example, there is very little variability in the fracture toughness. The variability in the curves is largely governed by the variability in the fatigue threshold. This now enables us to compute the worst case mean minus 3 sigma curve for this particular adhesive, which is shown in red in the figure. This now leads us back to the questions. How can we compute the growth of cracks in adhesively bonded structures under operational flight loads? How can we account for the variability? What's the controlling parameters? And how important is this variability on the economic life of the airframe? To address some of these questions, let us examine the growth of small naturally occurring cracks in the double overlap joint shown in this slide. This joint was tested under constant amplitude loading, and the figures shown here are taken from reference 5. The relationship between the energy release rate and the crack length is shown on the right-hand side, and using the Hartman-Shively equation with the constants D, N, A, and the threshold as shown in the slide, we show the comparison between the computed crack growth history and the measured crack growth history, the measured history being in blue diamonds. We also show what happens if the threshold is reduced slightly. And as you can see, a small reduction in the fatigue threshold produces a moderate reduction in the number of cycles to failure. To continue this study, let us consider the same joint subjected to a full-staff flight load spectrum, which is a combat aircraft spectrum. We will consider two maximum stresses in the spectrum. The first case when the maximum stress is 134, the other at 193.5 megapascals. The 193.5 corresponds to a maximum stress that you could realistically expect to happen in Owing skin. The number of flight hours, the load block is 200, and we considered the effect of a threshold of 5.6 and 7.1. As you can see, reducing the threshold to 5.6 produces a significant reduction in the number of load blocks to failure. The large number of small amplitude load cycles in the four-staff flight load spectrum results in the service life of the specimen being a relatively strong function of the fatigue threshold. This reinforces the need to perform sufficient tests to capture the variability in the fatigue threshold and hence to determine a statistically valid upper bound crack growth curve where the variability in the crack growth rates for the adhesive is taken into account. Thank you very much.